You can go ahead and get out your bell ringers at this point and start the new bell ringer for Unit 3, which is nuclear chemistry. And go ahead and answer this question, thinking about what the word nuclear means and what would be located there. Today we're going to talk about the difference between nuclear fusion and nuclear fission. Then in the future we're going to be talking about half-life and what it is, as well as solving problems using half-life. Nuclear chemistry refers to stable versus unstable isotopes. So one thing to keep in mind is one single element can have both stable and unstable isotopes. It is possible that one version of the element or one isotope of the element is completely stable and not radioactive or nuclear, whereas another version or another isotope of that same element with the same number of protons might be unstable and cause nuclear decay. For example, carbon-12 is stable and there's no nuclear decay. It's considered to be stable because there's approximately equal amounts of protons and neutrons located in the nucleus. We'll get more into that in a little while. Carbon-14, however, with a mass number of 14 is unstable and considered to be radioactive. Basically, this means that the nucleus of carbon-14 is not happy, essentially, and it will actually break down. Once it starts breaking down, it will release massive amounts of energy in the form of radiation. There's a special force inside the nucleus. It's called the strong nuclear force. It's going to hold the protons and the neutrons together. Now, a couple things about this particular force is, one thing is it only occurs over a very short distance. This works out okay if the nucleus is the right size, because the nucleus should be relatively small and compacted. Remember, we talked about the density of the nucleus. It's the most compact area of the atom. So the fact that the strong nuclear force only occurs over a short distance isn't normally a problem. However, the strong nuclear force also allows the neutrons and protons located within one nucleus to possibly attract other neutrons and protons depending on how far away they are. It's interesting to think about that because protons should repel each other since they're the same charge, but the strong nuclear force kind of overcomes the other force that we'll talk about called the electric force. So things to remember, neutrons have no charge. They're not going to repel each other, and they're not going to repel the protons. Since they're uncharged, their only main purpose in an atom is to contribute to the mass. Protons will repel each other with the electric force. That's the same force that allows the attraction of protons and electrons. It's the same force that causes the repulsion of electrons to other electrons. But protons will attract each other with what we call the strong nuclear force. So when we're talking about radioactive elements, essentially we're talking about the relative size of the strong nuclear force and the relative size of the electric force. It depends on which one is bigger. If the strong nuclear force is bigger, the nucleus will be stable. It will stay intact. It's not going to break apart. But if the electric force is bigger, that force of repulsion, then the nucleus is going to break apart, and that's what causes radioactivity. In stable nuclei, there's the attractive forces. The strong nuclear forces are stronger than the repulsive forces. Those are the electric forces that we just talked about. This graph right here shows you what's called the belt of stability. The belt of stability is essentially the ratio of neutrons to protons where it's considered to be a stable atom. We're going to talk a little bit about what's going to happen if the balance is out of sorts, if there's above the belt of stability or below the belt of stability, what exactly is going to happen. So when we talk about the balance of protons and neutrons, there's a couple of things to consider. The first thing is, if there's too many neutrons in a nucleus, the nucleus is going to be too big and the strong nuclear force is not going to be able to hold it together because the strong nuclear force, again, occurs over a very short distance. If you have a large nucleus, that strong nuclear force essentially can't hold on because the nucleus is now bigger. It takes up more distance than the strong nuclear force can act. If you have too many protons, then the electric force is going to be too large to overcome the strong nuclear force. Essentially, you're going to cause too much repulsion, and the nucleus is just going to break apart as a result of the repulsion of protons to protons. So you can see why it's important to have that fine balance between protons and neutrons. We consider the neutrons to be kind of a buffer between the protons, making it so they don't have to be right next to each other, but they still have to be pretty close to each other. So that's what the neutrons do. But if you have too many neutrons, you're going to have too large of a nucleus. Therefore, that strong nuclear force isn't going to be able to hold on. The nucleus is just going to fall apart. So from either extreme, too many neutrons or too many protons, you could get a radioactive element, an unstable isotope. So one type of radioactivity is called nuclear fission. Okay, so fission is defined as being the process when a nucleus splits into two or more smaller fragments and it releases neutrons and energy. So as nuclei split apart, essentially you're going to release some extra neutrons, and then you're also going to release some energy. So when you release that energy, that massive amounts of energy, that is the radiation that gets released in nuclear fission. So nuclear fission is taking essentially one big heavy nuclei, it's called, the larger nuclei, and you're going to produce what we call lighter nuclei, smaller nuclei. So if you imagine something like, for example, if you imagine uranium-235, if you shoot some neutrons from a special gun, essentially, at uranium-235, it's going to cause that uranium to have an unstable nucleus. And as a result, you're going to produce two nuclei that are smaller. And in these two nuclei, essentially, you get barium and krypton based on their atomic numbers, based on the number of protons that are found in each of the resulting two elements. In addition, you get extra neutrons released, as well as the energy, which is the radioactivity or the radiation released from that reaction. Every time you divide a nucleus, approximately 3.2 times 10 to the negative 11th joules of energy is released. This is, kind of dependent on the nucleus that's being divided, but that's kind of the general trend for dividing atoms and how much energy gets released. Another thing to keep in mind, that energy that's released, some of the mass of the particles before the reaction is actually turned into energy after the reaction. So you literally take some mass, like neutrons, and you literally just turn it into energy. This is the whole idea behind the matter to energy conversion, is the whole idea behind the Einstein's equation of E equals mc squared, where E equals energy in joules, m equals the mass, and c equals the speed of light, which is the constant, okay, at 3 times 10 to the 8th meters per second. So Einstein came up with this equation to show us if you have a certain amount of mass, how much energy actually will come out of that mass to energy conversion. What this results in, a small loss of mass, means a great amount of energy that's given off, because you're always multiplying it by c squared. You're always multiplying the amount of mass lost by the speed of light squared, which is a large number. So you can have a tiny amount of mass and still have a large amount of energy due to the fact of mathematically it's being multiplied by c squared. 3 times 10 to the 8th times 3 times 10 to the 8th, which is a huge number. And that's why you can lose a little bit of mass and get a lot of energy out of it, which is part of the danger of nuclear fission. Small release of mass still gives you a lot of energy. On the other hand, you can also have nuclear fusion. Okay, nuclear fusion is the opposite of fission. In nuclear fusion, you take lighter nuclei, smaller nuclei, and you combine them at extremely high temperatures. The result is a big nucleus, one large element, and a lot of energy being released in that process as well. So again, this is the opposite of fission. We're taking two small things and we are combining them to form one big thing. Now, this takes a lot of energy. Energy can be obtained during the fusion process, but the actual process of causing fusion to occur is going to take energy itself. Nuclear fission, however, doesn't take as much energy to begin, but it also doesn't release as much energy. So you kind of play a game there. So nuclear fusion is the one that's found in the stars and in the sun, and this is the energy that is produced when you actually take hydrogen nuclei and combine them. So remember, hydrogen nuclei are simply made of one proton, and then you have an electron floating around on the outside. But when we talk about nuclear fusion, we're only concerned about the nucleus. So hydrogen nuclei combining essentially takes two things that are one proton, and you combine them together to get one thing that now has two protons. So essentially you take two hydrogen atoms, you combine them together, and you create a helium atom. And this is what makes the stars and the sun. This is what gives us the radiation from solar objects. The reason that you need a large amount of energy to start this reaction is because of the fact that there's still those electric forces. Those protons that are in those nuclei do not want to be forced together. So you have to provide enough energy to overcome the electric force in order to force those nuclei to stick together to create the new element and create the actual fusion reaction. The energy that you need is usually provided by a high temperature. This is why fusion is almost impossible to do on Earth as it stands, because of the fact that you have to have such a high energy. It's possible, it's been done, but we haven't been able to figure out an easy way, a cost-efficient way to use nuclear fusion to actually produce power. The problem with this is nuclear fusion produces a lot more power, and you also get less radioactive waste, whereas nuclear fission produces the radioactive waste, but it doesn't give us as much power essentially coming out of it. So nuclear fission is important because it's easier. We don't have to provide the high energies to get it started because it's more of a natural reaction. All we have to do is shoot some neutrons at it to cause the element to become more unstable and kind of trigger that reaction. Once we've done that, the fusion reaction kind of has a chain reaction that we'll talk more about when we talk about nuclear power plants, but we get energy out of it from just a simple beginning of shooting a neutron at it. Nuclear fusion, however, you have to provide a lot of energy at the beginning. You get a lot more at the end, but how do we get the energy at the beginning is kind of the problem that scientists are running into. So now we know
is the amount of energy it takes to completely separate the protons and neutrons, collectively called nucleons. There are two forces acting inside the nucleus of atoms. The nuclear force, a residuum of the strong force that holds quarks together, is pulling the neutrons and the protons together, and the electric charge on the protons is pushing them apart. The strong force is a lot stronger than the electric force at short ranges, up to 2.5 times the proton diameter. But at larger distances, the electric force dominates. So as we add nucleons and work our way up the chart of the periodic table, initially each nucleus is generally a little more tightly bound than the one before. This chart gives the actual numbers. This increase in binding energy continues until we get to iron and nickel, where the nucleus has about 60 nucleons in it. At this point, the nucleus has a radius more than 2.5 nucleons wide, which you remember is the range at which the repulsive electromagnetic force begins to dominate. So as we add nucleons past this point, the electric force trying to tear the nucleus apart starts winning, and each added nucleon is a little less tightly bound. When we get to lead and bismuth, and the nucleus contains 207 nucleons, the electric force wins, and the atomic nuclei larger than this are unstable and come apart by themselves, although it may take a while. These larger nuclei can return to more stable arrangements in several ways. They can convert neutrons into protons and give off beta radiation, or kick out whole groups of nucleons, 4 at a time, in alpha radiation. Or they can simply split into other smaller, more stable nuclei. When this happens, we call it fission. Fission is different from the other forms of decay because it can be harnessed and controlled via chain reaction. Now let's consider what this means from an energy perspective. According to the binding energy chart, uranium has 7.6 MeV of binding energy for each nucleon, for a total of 1,786 MeV. while barium-144 has 8.3, and krypton-89 has 8.8. And the extra neutrons have no binding energy. So every time a nucleus of uranium fissions, we get about 192 MeV of energy. But U-235, left to its own devices, might take billions of years to decay. So we will want to help it along. We do this by shooting a slow neutron into it. It absorbs the neutron and briefly becomes U-236. Then it splits into krypton-92 and barium-141 and 3 free neutrons. Those 3 neutrons go to split other U-235 atoms into other daughters of more neutrons, and the process grows and repeats again. We can put the whole thing in water, and the daughter fragments and neutrons will be slowed by the water and cause it to heat up. Finally, we can use the steam to make electricity. This is how a nuclear power plant works. Ever since Einstein demonstrated the equivalence of mass and energy, physicists often give the rest mass of tiny particles like protons, neutrons, and electrons in units of energy. 2 convenient energy units are the electron volt, or eV, and its cousin, million electron volts, or MeV. Using these units, here are some facts that will come in handy. The rest mass of the proton is 938.272 MeV. The rest mass of the neutron is 939.566 MeV. Let's take another look at the chart of binding energy of atomic nuclei. And now let's talk about fusion. If we can take a nuclei of deuterium, which has 1 proton and 1 neutron in its nucleus, and get it to fuse with a tritium nucleus, which has 1 proton and 2 neutrons, we would end up with helium, 1 extra neutron, and some energy. And we would have the basis for an energy-making machine. Let's run the numbers and see how it works. The binding energy for deuterium is about 2 MeV. And the binding energy for tritium is about 8 MeV. So the total for the input items is 10 MeV. The binding energy for helium is 28 MeV, and the free neutron has 0 binding energy. Subtracting the 10 MeV from the 28 MeV reveals that every time this fusion happens, we liberate 18 MeV of energy. And that's pretty good. But there's a problem. Getting the protons and the deuterium and the tritium close enough together so the nuclear force fuses them together is hard to do on Earth. This is the energy that powers the sun and the stars. But the sun's gravity holds the fuel in place, while the high temperature gives the nuclei enough speed to overcome the electric repulsion. If we could make a miniature star in the lab, a microsun, then we would be well on our way to having a great solution to our energy problems. And although this has proven difficult, significant progress continues to be made. Similar to tritium is an isotope of helium called helium-3. It could be substituted in the above reaction and would produce a similar amount of energy. What's the difference? Well, there's an estimated 1 million tons of easily mined helium-3 on the moon's surface. It would only take 25 tons to satisfy all the energy needs of the United States for an entire year. And 25 tons also happens to be the maximum payload of the space shuttle. And now you know why we're going back to the moon.
The difference between nuclear fusion and nuclear fission, where each are found. And what you need to do at this point is go ahead and take a look at your new homework packet. You're responsible for completing parts 1 and 2. Make sure you take a look at the notes on Moodle underneath the test link. So there's a couple of questions that need to be changed or altered. So make sure you check those out. Hope you all did well on your test.